Hello, my persistent AP chemistry students. Welcome back. We're going to spend this video talking about electron configurations. And what would be helpful before we make this transition from all these quantum numbers and orbital diagrams to electron configurations is if you pause the video here a moment and fill in these orbital diagrams for the elements that are on your screen. I'm going to pause my video and do the same. And then we can talk about electron configurations. Okay, so there you can see all of my orbital diagrams. I have filled each box, each orbital with 2 electrons. If an orbital holds 2 electrons, I have spun one up and the other one spinning down. For my degenerate orbitals, which would be my 2p orbitals, those are the only orbitals up here that are at the same energy level. If I have more than one electron in my 2p orbitals, I have spread them out until I can't spread them out anymore, and then they start to pair. So we've talked the last couple days on how to draw these orbital diagrams. So an electron configuration is just a shorthand way of writing these orbital diagrams so that you could type it into like a line on a sentence, for example. We spent a lot of time on electron configurations in chemistry last year, and so I'm not going to spend a whole lot of time on them. But if you don't feel comfortable with these after doing the practice, definitely come talk to me and we can walk through a couple examples until you're comfortable with this. All right, so again, we're just writing the shorthand way of writing our orbital diagrams. So you want to, in each section, you want to indicate the energy level, the shape, and then the electrons that they're holding. So every single part of this code is going to have 3 sections to it. You're going to have your energy level, which is your N quantum number. You're going to have your shape, which is your L quantum number. And then this superscript is going to be the number of electrons in that subshell. So we are doing this by subshell and not orbital. So the 2p's will all be listed together instead of being listed as 3 separate orbitals. So if you want, we can do a couple together and then you can pause and try a couple on your own. So helium is going to have electrons in the first energy level, the second, the S shell, and it's going to have 2 electrons there. Lithium will have electrons in the 1s. It'll have 2 electrons there. It will also have an electron in the 2s suborbital. Oops, and it won't have 2 electrons there. It'll just have 1 electron. Okay, so go ahead and pause your video. See if you can write the other ones out, and then you can compare them to what I write out. Beryllium will be 1s2, 2s2. Boron will be 1s2, 2s2, 2p1. Carbon will be 1s2, 2s2, 2p2. Notice how I group the 2p orbitals together and I don't write them separately. Nitrogen will be 1s2, 2s2, 2p3. Neon will be 1s2, 2s2, 2p6. Sodium will be 1s2, 2s2, 2p6, 3s1. All right. Questions about that? Is it all coming back to you now? Hopefully. All right, so here's our next page. Again, I'm going to pause this and draw out all the orbital diagrams. If you want to do that, you can as well if you would like the practice on this. But what we want to transition to is starting to write these electron configurations by looking at the periodic table and not needing to write out the orbital diagrams first. So let me pause and draw them out so that we have a comparison. Okay, so here's the orbital diagrams for these elements. Notice they're all in the 4th energy level. And so we're going to have the 4s subshell with some electrons in it. Some of them have 3d and some of them have electrons in the 4p subshell. So notice the difference between potassium and calcium. They are both going to be found in the 4s block. And the difference is just a number of electrons in there. Notice the difference between scandium and titanium down here. Remember the 3d orbitals, just like the 3p or the 2p orbitals, they're degenerate. They're all the same energy level, so electrons will spread out through them if they can. And then notice that gallium here, you're going to add an electron for the first time into the 4p orbital. Now, we could write out the electron configuration for potassium, I would write out something like 1s2, 2s2, 2p6, 3s2, 3p6. Since all of those shells are full of electrons, I can automatically write those. And then I write 4s1. Right? Because that's where the last electron is. Now, notice that this part of the electron configuration is the electron configuration for a noble gas. Can you go find out which noble gas that's the electron configuration for? And notice it fills up the 3p shell. It has 18 electrons that it contains there. So that's the noble gas electron. That's the electron configuration for the noble gas argon. And so instead of writing out the whole noble gas, what we can write is called the noble gas electron configuration, where you put the noble gas argon into brackets and then you write whatever is left over after that noble gas. You write that after the brackets. So potassium's noble gas electron configuration would be argon in brackets 4s1. So this would be another good place to pause the video, see if you can write out the noble gas electron configurations for these elements. Dig deep in your brain. Remember this from chemistry. See how you do, and I'll do the same. All right, calcium would also start with argon 4s2, since it has that extra electron. Scandium would also start, its closest noble gas is argon 4s2, 3d1. Titanium would be argon plus 4s2, 3d2. Zinc would be argon 4s2, 3d10. That D shell is filled. And then gallium would be argon 4s2, 3d10, and then 4p1. Notice I am following the order of filling that we talked about in the last asynchronous video. And that's really, really important to do once you get into this 4th shell and beyond, because it doesn't just follow the numerical order. Okay, so those would be my noble electron configurations. Notice the only thing I'm allowed to put in brackets is a noble gas. I can't just pick the last element or any element I want to. The only thing you can put into a bracket is one of the noble gases. Okay, let's clear this and go on to the next page. We will go through these questions together. Okay, so again, here is your energy level fill order. And I just wanted to reference this one more time because of the noble gas configuration. So if we're looking at potassium again, potassium has 19 electrons. I'm going to start with the noble gas that is right below it. So I can't use krypton. Krypton has 36 electrons. That's more electrons than I have when I'm dealing with potassium. I'm going to use argon, which has 18 electrons. So again, for if you're using the periodic table to write out these electron configurations, you're going to write argon in brackets. That's this one. And then here's potassium. It's in the 4th energy level. It's in the S block, and it's 1 element over. If I'm writing galliums, let me do that exact same thing with gallium, which is here. I have 36 electrons. So I'm going to go look for the noble gas that is the closest to 31 without going over. And again, we talked about how that's argon. Okay, and then I just count over. Okay, these two are in the 4th energy level. They're in the S block, and there's 2 of them. And then notice this is the D block. And remember, the D block electrons follow the 4s. So it goes 4s and then 3d. So scandium is not 4d, even though it's in the 4th row. The d orbitals are offset by 1. So I would have to write that as 3d. And then if I'm counting to gallium, I count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then gallium is, again, the next one to fill is 4p. So 4, it's in the p block, and it's 1 over in the p block. That would give me gallium. Just like the d orbitals are 1 down from the row that they're in. So like this scandium is in the 4th row, but it's going to be putting an electron into the 3d orbital. Similarly, the f orbitals are down by 2. So this, even though you're in the 6th row right here, right? It's not 6f, it's 4f. And if we compare that to our chart on the side, 4f is going to fill right after 6s. So remember those 2 catches when you're using the periodic table to fill in these electrons. Okay, we're going to go through those questions together. Electron configuration exceptions. There are multiple exceptions. You really need to know 2. So to explain these exceptions, we need to look at where they are in the periodic table. And so if we look at a periodic table, krypton, molybdenum, copper, and silver. I'm actually going to go up so we can see these on the periodic table. Oh, it's frozen. All right. These 2 right here are an exception. All right, so notice if we were writing the electron configuration for krypton, we'd start with argon. And then we would go over 4s2 and then 3d 1, 2, 3, 4. So notice this would probably be what we would write for krypton. Molybdenum would be really similar, only it would start with Kr and it'd be 5s2, 4d4, right? Now, here's the deal. We've talked about how there's this special stability that happens when all of the orbitals are filled, and that's what happens with the noble gases. If we look at any of the noble gas electron configurations like neon, what we see is every single one of their orbitals is completely filled. Every energy level is completely filled. And this gives our noble gas that very special stability that we talk about. That's why they're noble. They don't associate with commoners, right? They don't bond with anything. They don't react. They're very, very stable all by themselves in their own little world, because this special stability comes from their energy levels being completely filled. Well, a very similar stability comes from a half-filled orbital. So if you look at the elements that have a half-filled orbital, there's this special stability that gets attributed to them as well. It's not quite as stable as the noble gas, but there's definitely a difference. And so look at this electron configuration. If we take an electron out of the 4s shell and put it into the 3D shell, we can have an electron configuration that is half-filled. Instead of being completely filled, nothing, super random, no pattern whatsoever, we can establish this pattern of half-filled, and achieve some special stability. And so chromiums, was I saying chromium the whole time? I feel like I was saying krypton. I meant chromium. Okay, so chromium's electron configuration is not what we would predict it to be. It is an exception. It would be AR 4s1 3d5. And in the same way, molybdenum would be Kr 5s1 4d4. So that's one of the exceptions. The other exception happens with zinc and then cadmium over here. So let me write out their noble gas configurations. Zinc would be argon 4s2. Oh no, just kidding, not zinc and cadmium. Copper and silver. Those are other two exceptions. Okay, 4s2, 3d9. And then silver is going to be Kr 4s2. Nope, my goodness. 5s2 4d9. Okay, there we go. So I want to give you a chance here. Pause the video and think of this idea of this semi-stability that happens with a half-filled. Can we, with a half-filled subshell, with a half-filled energy level, can we manipulate this one somehow in a similar way to the chromium and molybdenum elements and achieve that either special stability from a whole or from a half? And hopefully what you saw is we can do a similar shift of electrons. So zinc's electron configuration is not what we would expect. It's going to be argon 4s1 3d10. So notice, instead of having a full subshell and some random number, we can have a half subshell, a whole subshell. Half filled, completely filled, which gives better stability, lends better stability than some random number in there. Similarly, for silver, we're going to end up with Kr 5s1 4d10. So that electron just gets promoted. It's actually more like an excited state, but the excited state is more stable in this case than the ground state. So again, there are a couple more exceptions, but these are the four that you should be aware of, which it's really two. It's just kind of an exception for a family. And fun fact, this also explains some of those ions that we had to memorize before, like copper. Notice if you look at copper's electron configuration or silver's electron configuration, all of a sudden now we see why they both tend to lose one electron. Where do they lose that electron from? They lose it from their S shell. And so they both become a copper 1+, a silver 1+. Whereas if you look at the expected energy levels that don't actually exist, they really don't give any insight into those charges whatsoever. So it's kind of cool if once you start learning a little bit more about the periodic table and the exceptions that form and those special stabilities, it lends some explanation to things you may have had to just memorize before. Periodic table is so cool. I love it. Okay, so let's look at ions now. If we look at ions, we can write electron configurations for ions as well. Let's start with lithium. I'm going to write the electron configuration for lithium all by itself. 1s2, 2s1. Now, an ion of lithium, we know that the ion of lithium that forms is Li+, which means it loses one electron. So when atoms are going to lose or share electrons, they're always going to lose the electrons that are farthest away from the nucleus. As electrons get farther away, they're not attracted as strongly, and so those electrons are going to be shared or traded first. So lithium is going to lose its outermost electron, its valence electron. So the electron configuration for lithium plus would be 1s2. The configuration for anions is similar. So if you start with sulfur's electron configuration, let's do its noble gas configuration and save ourselves some work. 3s2, 3p4. All right, so sulfur, forms a 2- ion. That means it's going to have 2 extra electrons, and those extra electrons are going to fill in just like normal electrons will to fill the lowest energy state possible. So those 2 extra electrons are going to go into the 3p subshell. So sulfides electron configuration will just have 2 extra electrons, like that. And notice for these ion configurations, they are similar to one specific family. What family is that? And hopefully what you said was it's noble gas. So ions are going to lose or gain ions until they form a noble gas configuration. And this goes back to what we were just talking about with that stability. There is a special stability that happens when energy levels are completely full or completely empty. And so atoms are going to tend to lose or gain electrons until that happens, which leaves them with noble gas configurations. And this is what we would call isoelectric species. I think I have this on the next slide. Right. Isoelectric species are going to have the same electron configurations. Iso means what? It means the same. So their electric structure or their electronic structure is the same. So take a look at these. Which of these 3 has the same electronic structure? I would pause the video till you figure this out. And hopefully what you said is lithium, helium, and H-, they all actually have isoelectric configurations. Lithium starts with 3 and loses 1, so it's going to end up with 2. Hydrogen starts with 1 and gains 1, it's going to end up with 2. And helium just starts with 2. So all of these are isoelectric. Let's look at these down here. Calcium is going to start with 20 electrons and it's going to lose 2, which gives it 18. Leaving it with the same electron configuration as argon, not neon. Neon has 10 electrons, not 18. Sulfur is going to gain 2. So it starts at 16, gains 2 to become 18. So calcium and sulfur, the calcium ion and the sulfide ion are isoelectric, but neon is not isoelectric with them. Again, every ion will be isoelectric with a noble gas. Okay, so in this next little section, we're going to review the periodic properties of the elements and a couple tools, a couple properties that you'll find within the periodic table itself, along with some things that you can kind of use as tools. The more you learn about the periodic table, the more powerful a tool it is for you. So we're going to talk about some of these properties. Just a quick history so that you don't think that the periodic table went poof and just appeared out of thin air. The elements, there were about 8 metals that were known as kind of the most basic structure it could possibly be. They couldn't break them down any further. And they knew about these 8 elements in the ancient time. All of them were metals. In the Middle Ages, when they were trying to make gold, they discovered about 6 more. And then between the years of 1735 and 1843, 42 more elements were discovered. And so at this time, you can kind of see the progression after that. At this time, they started really needing a way to organize these elements. And they also started noticing some patterns among the elements. And so the race was on to develop a functional way to organize the periodic table. We talked about a couple of these guys last year in chemistry. So Meyer and Mendeleev, they both proposed a periodic table with the same format. Mendeleev actually took that format, though, and predicted properties, left spaces in the periodic table, and he predicted the properties of the elements that would someday be discovered and fill those spaces, which was pretty amazing. He predicted a couple elements that weren't actually discovered until, years and years and years after he died. So he was actually posthumously given the Nobel Peace Prize, which was kind of cool. There was a third person, Moseley, who was also trying to organize the periodic table, but he organized the periodic table based on atomic number instead of atomic weight. And so he actually kind of took the lead, he had an advantage over those other two, because if you look at atomic weight, there are a couple of elements that get flipped. And our current periodic table is organized off of atomic number, so protons. And when Moseley made this switch from organizing from atomic weight to organizing with atomic number, he actually fixed some of the mistakes, and all of these patterns just kind of fell into place. So our current periodic table is organized by atomic number, and then every time the reactivity repeats, that line of elements is cut and shuffled underneath. So we get this atomic number going sideways, reactivity going top and bottom. Okay, so when we are talking about energy levels, one of the graphs I want you to be aware of is the graph that you looked at in that little exploration for covalent atoms, covalent molecules. And so when you're talking about electrons and its location to the nucleus, what you want to think of in terms of energy is potential energy. So again, think of that stack of books. The higher my stack of books, the more unstable my system. The lower my stack of books, the more stable my system. right? If I'm going to carry food through a restaurant on a tray, I want to have a very low center of gravity with all of the food kind of spread out around that tray. I don't want to stack all the food up super high because there's a much higher likelihood that I will drop all of it in the middle of the restaurant and it will make a giant mess and I will go cry in the side room and until my stress is gone, right? So lower energy, lower potential energy equals more stability. And so what we see is as we look at the shells, we see that kind of a graph that you saw in that activity where when the electron is too far away from the nucleus, the potential energy is not as stable as it could be because there's going to be an attraction that happens. When the electron is too close to the nucleus, it's also not as stable as it could be because there's going to be a repulsion that happens. And so there's this like happy distance between the nucleus and the electron that occurs. And that's where our energy shell is going to be. Now, as you look at other energy shells, so let's say this is our 1s shell. If we look at a second energy shell, a 2s shell, what we're going to see is that that lowest potential energy point, that dip, is going to happen closer to the nucleus. But then we're also going to get like a node where our first energy shell happens because those electrons will push away the 2s electrons. We'll get another dip in energy level and then it'll go back up. So you can kind of tell the number of shells by the number of like potential energy dips it has, because that's how many shells are in front of it and going to have an effect on the repulsion of those electrons. Okay, so at this point in time, I want us to think about the trends that we have talked about before, the periodic trends. Actually, I'm going to go back up a slide just because it's going to give me a little bit more space. So I want you to think about the periodic trends we talked about last year and see if you can recall these and what the trends were and why the trends occurred. Okay, so we're talking about atomic radius, ionization energy, electronegativity. Your book might talk about electron affinity, and electron affinity and electronegativity are very close concepts. And the one I really want you to grab a hold of is electronegativity. Okay, there is one more that we'll talk about, which is the ionic radius. But let's get through these three big ones, and then we can talk about ionic radius after that. Okay, so atomic radius, what does it do left to right? What does it do top to bottom? And why? Now would be a really good time to pause yourself and see if you remember this and see if you remember the reasons that these things occur. All right, atomic radius. So our atom, as it goes left to right, is going to start big and get smaller, smaller, smaller. So if we're looking at the second row, lithium is going to be our biggest atom in our second row, and fluorine is going to be one of the smallest in our second row. And that's because, so it decreases, and that's because the number of protons is increasing, and that's where we get into Z effective. Z effective is increasing, 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 so the electrons are getting pulled in, pulled in, pulled in, pulled in, pulled in. Atomic radius top to bottom is going to increase. You're going to get bigger and bigger and bigger. So the smallest atom in the first column in that first family is going to be hydrogen. Your biggest is going to be francium, and that's because you're increasing in energy levels. Hydrogen has 1 energy level. Francium has 7 energy levels, and so that 1 valence electron that's there is going to just get kicked out to the 7th energy level, and that atom's going to be a lot bigger. Ionization energy is the energy it takes to pull off an ion, and that's going to increase from the left to the right. So it's the easiest, lowest ionization energy for lithium. It's the hardest to pull off an electron, highest ionization energy for fluorine. Again, that is because of the number of proteins. The Z effective is increasing because that number of protons is increasing. And so it requires more energy to take it off. Ionization energy top to bottom is going to decrease. And again, that's because you are increasing in energy levels as you go down the shell, and therefore you're increasing distance between the valence electron and the nucleus. When the valence electron gets farther and farther and farther away, it's easier to pull off. So there is a lower ionization energy. It takes less energy to remove the electron. Electronegativity is the attraction between the valence electron and the nucleus. And so electronegativity from left to right is going to increase. So the fluorine is going to be more able to attract an electron because it has more protons. It has a larger Z effective. Lithium is going to be less able to attract an electron because it has less protons. It has a lower Z effective. Ability to attract an electron. Okay, electronegativity top to bottom is going to decrease. So lithium is going to be more able to attract an electron. Francium is going to be less able to attract an electron. And actually, if we look at the halogens, it makes more sense. Fluorine is extremely able to attract electrons. It is the most electronegative element on the whole periodic table. And if you go down that family, as the valence electrons move farther and farther and farther away, like iodine, the electron on iodine is not as attracted to the nucleus because it's farther away. There's more shells in between. And so the electronegativity of iodine is going to be less than the electronegativity of fluorine. Okay, so there's your crash course. Remember all of this? So glad that we paid attention in chemistry. So glad that we put all that effort into learning this last year. I'm just going to talk through a couple details, and then in the next asynchronous session, we'll talk about ionic radius, and then we'll also talk about some general trends in reactivity in the families and the elements and the groups. Okay. Okay, so like I said, a couple details on those periodic trends that we just talked about. When you are talking about an atomic radius, it's defined usually by a bond. So usually when we're talking about an atomic radius, you take a diatomic molecule like nitrogen, and you kind of take the distance, you measure the distance between the two, and then if you divide it in half, that's how we define atomic radius. Now, not everything will bond to something else, like hydrogen, for example. We can't even force it to bond to stuff. And so that is going to be defined by a non-bonding radius. And so some of these discrepancies that you might find on different periodic tables or different atomic radius tables may be due to this difference in a definition. Obviously, a non-bonding radius is probably going to be bigger than a bonding radius. All right, we can do this practice together. We talked about atomic radius trends and the justification. We're going to do this practice together. We talked about ionization energy and the justification. Here is an example of how it will be written out. And here's your detail, your extra detail about ionization energy. Notice that there's a first ionization energy, which is the energy required to take off the first electron. And then there is a second ionization energy where you're actually taking an electron off from the ion. And so we call these successive ionization energies. They'll always get bigger. And if you look at a chart of these, you'll notice jumps when you have to go into a new subshell or a new energy level. There's a big jump. So for sodium, we would expect there to be a really big jump in between the first ionization energy and the second. Whereas for magnesium, which starts with 2 valence electrons, we would suggest that the big jump would be between not the first ionization energy and the second, but between the second ionization energy and the third, because the third ionization energy is going to take an electron out of a core shell. So with these ionization energies, you can actually predict a lot about the structure of an atom just by looking at how much energy it takes to pull electrons off of those atoms. And then, so again, we want to focus more on electronegativity than electron affinity. So we want to look at the attraction, the ability to attract an electron. The definitions are super close. We're going to focus on electronegativity. Okay, and then we get into metals. So when I see you next, we'll do some practice together. In our next asynchronous session, we're going to talk through common groups, patterns we see in groups of elements, and patterns we see in reactivity. Okay, good job. Send your questions my way. Have a great afternoon.